Right, hi everyone. I'm here to talk to you today about a NASA mission that hasn't been launched yet. It's a new mission to go and look at the Trojan asteroids, which are near Jupiter. And so the mission itself is called Lucy. You can see it's kind of lurking behind me in a very sinister way. And I'm going to tell you a little bit about what Trojan asteroids are, what the mission entails, and why you should be excited for it. So my name's Carly Howett. I'm the Assistant Director of the Department of Space Sciences, and I'm also an instrument scientist on the Lucy mission. So Lucy is a mission to look at some of the small bodies in our solar system. So this is our solar system. The sun is obviously not to scale. The sun's in the middle. We have the Earth and Mars. And then there's this group of, shown in yellow here, called main belt asteroids. And those are typically what we think of when we think of asteroids. But there are actually these other asteroids shown in purple here that lead and trail Jupiter in its orbit. So that they're at the same distance as Jupiter is from the sun, but they're sort of ahead and behind Jupiter as it moves around the sun. And we're going to talk about what these L4 and L5 points are as we go into the talk. But they're a special region of space that makes it particularly stable for these targets to hang out there. So it's a tour of the Trojan asteroids. We're not just going to one, we're going to go and look at a whole bunch. In fact, we're going to look at 6. And so it's a really low risk mission. We're flying instruments that have flown before, we're flying a spacecraft that's flown before, but we're going to look at something that has never been seen before. And I think that makes it particularly exciting. It's really a mission of exploration. And it's called Lucy because Lucy was a sort of a missing link in terms of, provided sort of a missing link in terms of human formation and evolution. And as I'll go on to show, we think that this mission can do the same for solar system formation. So this is Lucy. This is why this is on the title slide. These are the bones that were left out of Lucy, and we think she looked like this. But Lucy was really kind of a part of the missing link of how humans went from being sort of more ape-like to looking more humanoid. And so you can see she's walking on 2 legs. She's shorter than us, would be now, but starting to look much more like the people that we know today. All right. So why bother studying these asteroids? So small body populations are really interesting, and usually people know them as the first ones people think of are near Earth asteroids, in part because we've all seen Armageddon, right? So there's a possibility that eventually one of these near Earth asteroids comes in and it hits the Earth with terrible consequences. So one of the things that's been done a lot recently is trying to understand this population, and that's what this graph shows at the bottom. So the total number of discovered near-Earth asteroids versus their diameter. And you can see largely they're pretty small, so under 100 meters. The ones that are over 1 kilometer are much less numerous, thankfully. And again, the chances of them hitting us are very small, so let's not worry about it too much. 2020 has got enough to worry about without one of these. All right, the other thing that people know about are main belt asteroids. So these are, we already touched on these a little bit, these white objects that are between Mars and Jupiter. As you can see, there's lots and lots of them. We think there's sort of in the region of 1 to 2 million of them that are bigger than 1 kilometer. And despite the fact that they look very close together on here, actually the mean distance between them is many, many miles. So over 600,000 miles apart. So if you remember that scene in Star Wars where they're flying through the asteroid belt and Han Solo is doing amazing flying in his Millennium Falcon, swooping in and out the asteroids, yeah, he wouldn't need to be that good. They're very far apart. It'd actually be quite hard to hit one. Okay, so, and the Trojan asteroids are the things that we're interested in. So these are shown in green here. You can see Jupiter's in the middle. So some are known as, there's 3 different populations. They've all got little nicknames. So Trojans, which isn't very helpful because they're all technically Trojans, the Heldas and the Greeks. But I'm going to use the term Trojans to describe both of these populations. So this is a description of what the L points are. So L stands for Lagrangian, and basically they're points in space that are very stable because the gravity cancels out. So this is the Earth. All bodies will have them with the sun, and it'll just depend exactly where they are, just depend on the mass of the body. So if we look at the Earth, it has an L1 point, which is pretty close to the Earth, where the mass of the sun and the mass of the Earth cancel out. And then the same the other side of the Earth too. We have one, diametric opposite side of the Earth, and then at this 60-degree angle between the sun and the Earth. And basically, these are regions in space. So if you put an object in one of these points, you don't need to do much to keep it in that region. So they'll happily sit in that. It's not going to spiral into the sun. It's not going to spiral into the Earth. It would be very happy. And again, this isn't to scale, but it's just to give you an idea. So this L4 and L5 point is a stable region in space, which is really important because it means that whatever's captured there could have been there for a very long time. We don't really know how many Trojan asteroids there are. And what's interesting is because this region of space is so stable, they could have been remnants of early solar system formation. And I'm going to spend the next few minutes explaining that because it's not a particularly intuitive thing, why these and not others. Okay, so there's a model of the early solar system which was completely revolutionary in this century, and it explained a lot about the cratering record that we see. But I'm going to play this movie and talk through it as you go. So you can see largely we think that this model, it has Jupiter, Saturn, Neptune, and Uranus. So those people that remember their science, this isn't the way that the planets are now, right? But it is one idea of how they were formed. So all much closer to the sun than they are now, and in a different order. These green objects are sort of little planetesimals, and these colors indicate where those targets are. So this is Jupiter again, this is Saturn, Neptune, and Uranus. And then there's this major cataclysmic event that happens where everything gets unstable, everything goes haywire. You can see these little objects are thrown in and they're thrown out, and Neptune and Uranus swap places. And you end up with a solar system that looks a lot more like the one we have today. And this explains a whole host of things. It explains composition. It explains the idea that there was this region, there was this time whereby there was so much flying around our solar system and causing craters on targets. And this previously has been very hard to explain. So you end up with this kind of endpoint. So you end up with things being formed at different distances, and then this major cataclysmic event happens, and a little bit of each one of these different populations that all have different compositions because they formed at different distances from the sun, kind of go in and form this population that hangs out at Jupiter. It gets captured by Jupiter's immense gravity, and lots of others are lost. But there's this sort of sample that are kept from this very early solar system population. And this is what we think the Jupiter's Trojan asteroids may be. And that's why it's going to be so interesting to go and look at them. Okay, this is another model of the asteroids. And it just shows you that they're not all in that same plane. They're not in the same plane as the ecliptic, so as in Jupiter and Earth. They actually move up and down through that plane. And this is just kind of a model showing you that they're dynamic, and it's going to be a really interesting swarm to fly through. So what do we know about them? The answer is not a whole lot. So this is a pretty crude graph, but it gives you kind of an idea of what I'm talking about. So this is just wavelength. This is visible to infrared, and reflectance is just how good it is at reflecting sunlight. And you can see that the D types do a pretty good job at reflecting sunlight, much better than the P, which is better than the C. So the D types are kind of red, we call this. These are kind of, the C types are gray. They don't do a good job at any wavelength reflecting. And the P types are kind of sort of split the difference, right? They look like a little bit of one or the other. We also know that you get different amounts of D, P, and C types at different sizes. So if you look at all of the asteroids that are between 20 and 50 kilometers, you see a lot of P, a little bit of D, and a little slither of C. But if you move to between 50 and 100 kilometers, then this really changes. You get no P at all, lots and lots of D, and a kind of a bigger wedge of C. But if you get to really big ones, then you see they're almost split between D and P with no C at all. So we don't really understand what's going on here. Like, why is there no P in this? Why is there no C in this? We don't really know. And so by going and looking at these targets, we'll have a better idea of what's going on. One of the things that we also have been looking at is how the mass of these targets, so mass is this way, changes as you move from distance from the sun. So 5.2 is where Jupiter hangs out. And you can see that it's not just a single peak, right? So actually the C types and the P types actually have a little bit of a spread of where they're located. So they're not just right of Jupiter, they're a little bit inwards of Jupiter and a bit outwards of Jupiter. And that seems to vary with mass too. And we don't really understand why they have these distributions. This is just how much they reflect. Albedo is just a measure of reflectance. So visible albedo is sort of what your eyes could see almost. You could think of it like that, and how much visible light is being reflected. W1 is more in the infrared. So how much of the infrared light does it, will they reflect? And these are our targets shown in red. And these are the ones that we know about, the other Jupiter Trojan asteroids. And this is really just to show that we really are sampling a diverse types of asteroids. So we're looking at ones that don't reflect very much and then ones that do reflect a lot more. And we really want to understand what makes these different. What does a C-type mean? What does a P-type mean? What does it mean to have different albedos and different sizes? So we're going to compare all of the Trojan types, so a C, a D, and a P. And what's really interesting is they're all kind of co-located. And so we're going to be able to look at them in the same environment. So we're not looking at some that are much closer to the sun, some that are much further away. So it's really by looking at the diversity of the different Trojans that we're going to be able to understand sort of what their story is, what have they got to tell us. So let's go on and look at the mission itself. So we already talked about this. Lucy is a Trojan tour. It's got a 2021 launch. Actually, as I record this, today is the 16th of October, and the launch date opens, I think, a year today. So it's coming up hard and fast. Definitely look for it next year. You know, with COVID, it has been difficult. There have been delays. It's possible we could slip to the backup launch date in 2022. I certainly hope that doesn't happen. It's certainly not in the plan, but it is feasible, and we do have a backup launch opportunity. We have a main belt asteroid, so we're going to go past an asteroid that's in that main belt between Mars and Jupiter in 2025. This gives us a nice opportunity to look and test all of our systems out and just sort of do a kind of a rehearsal ahead of the main encounter. And then we have 5 Jupiter encounters over the course of about, what is that, 6 years, looking at a total of 6 targets. One of them is a binary, so I'll talk a little bit about that as we go. Okay, so what are we going to do? Well, one of the things we're going to look at is composition. So the color and the composition, and what is it made of? You know, is it made of ice? Is it made of minerals? Is it made of organics? Look at the geology. Is it heavily cratered? Do we see layering? Do we see other interesting structures on the surface? Sort of what's going on? What does its geology tell us about its history? And then trying to get at the interior. What's going on under the surface of these targets? And we're also going to be looking at rings and satellites. Rings happen when, you know, sort of get debris fields, and satellites could tell a very interesting part of its history. We think that one of the targets may have a satellite, so it'll be interesting. They're definitely feasible, and it'll be really interesting to see whether we find more. So this table just gives you an overview of the targets we're going to look at. So Donald Johanson is our main belt asteroid. So it's the first one we're going to look at. And then we have our main Lucy targets. So Eurybates is a C-type, Polymele is a P-type, Lucas and Oris are D-types, and then we have this Trojan binary that I'll describe a little bit more in a while, that are also a P-type. But just by looking at this table, you're going to get a sense of how different these different targets are. So of course, the main belt one is very small, but we also sort of under 5 kilometers, but then we got to hundreds of kilometers, 100 kilometers diameter in these targets. Their spin is just how quickly they rotate, some of which we don't know, some of which are very slow, 440 hours, so many days, Earth days. And on Polymele, very fast, so, you know, a fraction of an Earth day. They're all pretty dark, some of which are much darker than others. An albedo of 0.1 is pretty dark, you're talking coal. And so this is, all of these are much, much darker than that. Eccentricity is just how non-spherical their orbits are. And so you can see that those are different too. And then inclination is just how much is it tilted up outside of that plane that the Earth and Jupiter sit on. And so the higher the number, the more it's tilted. And you can see that there's definitely some differences there too. And then whether we know the pole and how the pole, and where the pole is located. So you can see there's a lot still to learn. So this is a very busy plot, and I'm going to explain it to you because I think it's pretty cool. So this is an overview of how Lucy is going to fly. So this is the Earth in the middle with the blue dot. Jupiter's out here, and the Trojans that we're going to fly through are out here. So in L4 and L5, which now, of course, we all understand what it is. Okay, so we start off, and our nominal launch date is October 16th, 2021. So a year's time. Beep. And so we launch successfully, of course, with no issues. And then we go out and we have this deep space maneuver. And then we come back in and we do another flyby of the Earth. So an Earth gravity assist, our first Earth gravity assist, almost a year later, exactly a year later, I guess. And that puts us on a slightly different trajectory. And then that pulls us out. So we're right out here now. We do another deep space maneuver that pulls us in to the Earth, where we have an Earth flyby again, another gravity assist. And then that puts us on our trajectory out. So we do a main belt encounter, this Donald-Johanson encounter, 2025. So just under 4 years from launch. And then we go on and we fly through the L4 swarm. So that's when we have all of our encounters between 2027 and 2028. So a really busy period for us then. And then we exit the L4 swarm and we kind of do a sort of almost like a figure 8 swing by back towards the sun and then out to the L5 swarm where we do our binary Patroclus and Menenius. And this is a really stable orbit. You can kind of sort of see it's going to do this sort of figure of 8 thing, right? And you can almost do this with spending very little fuel. So although our nominal mission ends in 2033, if the spacecraft's healthy and there's fuel on board, there's definitely going to be future opportunities for investigating more targets. So Eurybates is a really interesting one, and we think it's the largest member of a collisional family. So what we think happened was at one point there was a big something came in and smacked it, and it broke apart. And Eurybates is sort of the core of that was left, the sort of biggest chunk of that was left. We've never looked at an object like this, and it's going to give us a really interesting insight into how this sort of breakup works. The main belt asteroid is also kind of interesting. We've seen quite a few of main belt asteroids before, and so it's really going to be a nice way of testing our systems, but also we're going to be able to just look at a new target, which is pretty interesting. So how much is it cratered, for example? So this is where our target lies. As you can see, it's a little bit, semi-major axis is just distance from the sun, and AU is the distance from the Earth to the sun. So you can see it's about 2 and a bit times further out than the Earth is from the sun. H is kind of weird, like the lower you are, the brighter it is. So it's kind of on the brighter side of the main belt asteroids. We already talked a little bit about Eurybates, but one of the things I'm most excited about is this equal mass binary. And equal mass binaries we see in the solar system. So equal mass just means both targets, both objects have about the same mass, and a binary just means they sort of orbit each other. And we'll talk a little bit about how that works. We don't really know how they formed, which is kind of an interesting part of the puzzle, but we think that they must be very ancient. So you could imagine that this sort of system doesn't take much to disrupt it. If you have something come in and it would easily, if it knocked one or the other, it would they would stop orbiting one another. You'd disrupt this system. It doesn't take a lot to break it down. So we think it must be very old. It's very undisturbed. It hasn't been heavily bombarded and thus disrupted. Lucas is a really interesting target, and this is a light curve, which is a little bit hard to understand, but basically it's how Lucas reflects light as it rotates. And so if you have a very long target, so you think about banana, if the banana lengthways is looking at you, then it would reflect a lot of light, right? So that at that point you would see the peak in your banana. And as it rotates, and you're now seeing the banana from end on, say from the stalk down, it's now got a very small amount of area that's looking at you that can reflect the light. And so you would see a decrease in the peak. This can also happen just with albedo. If you have a really bright region on one side, it's reflecting a lot of light. And as that bright region moves away from where your viewing angle, the light curve goes down. You can't see it as well if you're just looking at the dark side. So that can explain this sort of bright up and bright down. So maybe it's shape, maybe it's color. Those things are hard to disentangle. It's typically shape. Most of these things are pretty dark, which sort of explains this, but this is really interesting. Like, what the heck is going on here? Well, we don't really know that other than maybe it has a really interesting shape, or perhaps it has a satellite. Maybe there's something else going on. And so thinking about it as just one object is not, makes it really difficult. And you can see each one of these symbols is a different observation. And it's by piecing them all together that you kind of put together this light curve. And that gives you a rotation period. When you kind of, when you try different rotation periods and you piece it all together, then you can start sort of building up these sorts of curves. It's a little bit complicated, but the fact that you get such a nice match by different observations kind of tells you you're on the right ideas. So this is an idea of what's going on with our targets. So this is just an artist's concept. So you can see Patroclus and Menenius, very big. These are our binaries. And then we have kind of much smaller targets. So these are our near equal mass binaries. And this is an idea of what they might look like. So again, these are all artist concept. This is an image that was taken with the Keck telescope using adaptive optics, or AO, which is basically just a way of helping mitigate turbulence in our own atmosphere, because this is the Keck is on Hawaii. And so you're looking through the Earth's atmosphere to these targets. But you can sort of see they don't orbit one. One doesn't orbit the other, but rather they sort of orbit one another. And so it's going to be really, really interesting to see something like this. We've already talked about the fact that we're looking at all the different spectral types in both swarms, so both the L4 and the L5 swarm. And there's 160 times difference in mass between Polymele and Patroclus. So these are very different targets, which is also an interesting problem for a spacecraft, because you can't tune your spacecraft to look at something very small or very big. It has to be very versatile, so it can do both. I already talked about how Eurybates might be a collisional remnant, so it's big. Maybe this is a fragment, so from a different collision, perhaps that's sort of a smaller bit from a different collision, and these might be primordial, so very, very old targets. We already talked through this. So these are some of the main belt asteroids that we've seen before. So you can really see that main belt asteroids come in all different shapes and sizes. Ceres is very large, almost 1,000 kilometers wide. Vesta is much smaller. Ceres has these really interesting white spots that we think are salts. And then these are not quite to scale, I think, here, but you can see that they do get very, very small indeed with these really interesting shapes. So it'll be interesting to see just how different the Trojan asteroids are to the main belt ones. So let's look at the observations and instrumentation. So looking at the remote sensing, so we'll look at the geology. This is Right Mons on Pluto. We think it's an ancient cryovolcano, so a mountain with a hole in, but where it wouldn't be molten rock, it would be frozen ice, water ice, or liquid nitrogen, frozen nitrogen ice that comes out of it. Color and composition, so what's going on its surface, how does the color vary, how does the composition vary? The interiors, like what's going on underneath, whether it's solid, whether it might have some fractures, whether it's kind of a rubble pile like boulders that are basically loosely gravitationally bound and then covered in dust, or whether it's just a conglomeration of very, very small gravel-like particles, whether it has satellites, whether it has rings, all those sorts of good things. So this is our payload. This is the spacecraft with 2 enormous solar panels. And the solar panels are going to be a really interesting development. So I do a lot of work in outer space missions, and this is my first one using solar panels, because usually they're nuclear powered, just because the light out of Jupiter and beyond is so weak. So these are enormous solar panels that you need because you're so far from the sun in order to make your instruments and your spacecraft work. So everything lynches on these solar panels. Without them, we don't get power. So upon launch, they'll unfurl. And we just had a test showing that they successfully unfurled on the ground. So fingers crossed post-launch. So these are our instruments. So we have Ralph, which is the color and the imaging infrared spectrometer, so the composition part of it. We have Latesse, which is the thermal, so how much heat is given off. This will be able to measure it. Lori is kind of our are binoculars in the sky, if you like. It's the camera that has very high spatial resolution observations. And then radio science, so how we communicate with the spacecraft, but also as this will enable us to determine how these targets pull on the spacecraft and move it as we fly past the objects, which will enable us to determine their mass. So this is an example of results we've seen from LORRI. LORRI was flown on New Horizons. This is an image that was taken by New Horizons. You're looking at water ice mountains against a glacier of nitrogen. This is an overturning region. It's super, super interesting and amazing image. This is returned from Pluto, so much deeper in the solar system than Jupiter is. This again is Pluto. Ralph also flew on New Horizons. This is an updated version of Ralph. It has an extra channel, so it has a little bit better color information, but it'll basically give us similar information, so color information on our targets. And this is just showing the coloration of Pluto. LISA is the infrared spectrometer. So this was an image that came out of New Horizons where we looked for water bands and we showed where on the surface they're located, and those are shown in blue here. So you can sort of see them along this ridge and on some of the regions, on the mountainous regions near this big glacier. We kind of end up with a spectrum like this where we can look at things like bands that are indicative of water. So you could think of these bands as like fingerprints. If you see them at certain wavelengths, you know that that's made by things like water or organics or minerals like phosphine. And then finally, LATES. So this is the thermal. And I think what that's going to tell us is when we're looking at a surface, this is kind of what we're looking for. So the cooler temperatures that you get at night, and then this warming during the day, and then cooling off in the evening. And it's really this sort of warming and cooling curves that can tell us quite a lot about what the surface is made of, what its albedo is, and what its thermal inertia, which is basically its capability of retaining and then giving out heat again. So it's telling us a lot about the surface. So I hope I've convinced you that Lucy is an exciting and upcoming mission. As we mentioned, it's a Trojan tour and it's funded by NASA's Discovery program. It's designed to understand the diversity of the Trojan system. So really a mission of exploration with a launch next year and a backup launch date the year after that. So our first rehearsal, the first data that will be kind of really interesting, I think, is in 2025. And we'll have some encounters that happen pretty quickly after that, so 2027, with a total of 6 Trojans looking at in total. So I hope I convinced you that you should love Lucy as much as I do, and stay tuned. If you want to understand and follow Lucy, there's a really good Twitter presence. So if you look at Lucy Mission, you'll see a lot of our developments, and especially as we get closer to launch, some really nice videos of the hardware being tested and integrated onto the spacecraft. And then in a year's time, it's launched. So stay tuned, and definitely as we move through launch into some of these encounters, I hope you'll be hearing about them in very positive ways, and you'll be able to think, see, I know all about it now. All right, thanks for your attention, and enjoy the rest of the con. Thanks. Bye.